So today we're doing the introduction to polynomial functions. So a polynomial is a function of degree n and is defined by a p of x or f of x is equal to a sub n x to the n all the way to your a sub 0. So this is your leading coefficient. So your leading coefficient is a sub n x to the n. Well, this is your constant right here. For n is a non-negative integer and a sub n are real numbers. So your a sub n cannot be equal to 0. Now, the leading coefficient a sub n is the coefficient of a term containing the variable raised to the nth power. Here are the different classification of polynomials. So if I have a degree 1, it's my constant polynomial. And a degree 1 is your linear, 2 is quadratic, 3 is cubic, 4 is quartic, and 5 is pentic. The characteristics of a polynomial function is smooth and continuous. There are no sharp turns, no cusp, or breaks on the graph. So this cannot be considered a polynomial function, or there is a sharp turn. So any piecewise of this form are not polynomial functions. There's a break on the graph. So those are not polynomial functions. Now also, there is exactly a number of roots or solutions, which can be real or non-real. So if the degree is 4, then there will be exactly 4 solutions. And there can be at most n minus 1 terms. So it doesn't mean that it has to, if the degree is 4, that there should be 3 terms. It could be at most 3. So it can be 2, it could be 1. So the most will just be 3. Now, the end behavior of the graph. So the graph of a polynomial function can rise or fall without bounds as x decreases to negative infinity or increases towards positive infinity. This behavior to the far left and far right is what we call the end behavior. Now, which determines the end behavior? It's the degree of your polynomial function. The degree is the highest degree, which is the degree of the leading coefficient. And your leading numerical coefficient determines the direction. If the graph is flipped upside down or not. So if the degree is odd, which means the highest exponent is odd, say for example 1 or 3 or 5 or 7, then they act in opposite end behavior. And the reason for that is if I have, say, x to the 3rd power and I'm plugging in positive x, so plugging in positive x will give me positive, which means that my y can go on forever to positive infinity. At the moment I plug in negative x to my x, now my y value can go to negative infinity. So that's why they can go in opposite direction for the end behavior. But if the degree is even, then the functions will have graph whose end behavior will go same way. So for example, if I have x to the 4th, and so on, if I plug in a positive x, I get a positive y value. If I'm plugging in a negative x, I will still get a positive y value. So they could exit the same way. The graph could end in the same way. Now, so this is a summary of our leading coefficient. So if your graph will have a positive leading coefficient, then it is even. Your graph will end going both to positive infinity. But if your graph has a positive coefficient, and it is an odd, then they go in opposite directions. So as x increases, your y is increasing. As x decreases, your y is decreasing. And if it's even, as x increases, your y is increasing. If your x decreasing, your y is still increasing. If the leading coefficient is negative, on the other hand, then your graph is flipped upside down. So both ways, in both directions of the end behavior, will now go to negative infinity. So as x increases, then your y is still decreasing. Your x decreases, your y is still decreasing. Now, if it's a negative coefficient and it's an odd exponent or odd degree, then as x increases, your y is decreasing, and as your x decreasing, your y is increasing. So that is how the end behavior of polynomial functions will be. So let's have it here with our example. So let's determine the end behavior of this given polynomial. So our p of x is equal to x to the fifth minus 3x to the fourth plus x cubed minus 2x squared plus x minus 1. Now the leading coefficient has an odd exponent. The leading term, I mean, and the leading coefficient is positive. So since this is odd and it's positive, then we know that as x increases without bounds, or as x goes to infinity, the y value will also go to positive infinity. But as x decreases, then your y value will also decrease. Right? Now, how about on the second example? So I think we have a typo there in your note sheets. So we'll change it to this example instead. So if our polynomial of x will be equal to negative x to the fourth plus 3x cubed plus minus x squared plus 1. So we consider that this is a negative leading coefficient. And we have an even exponent, because it's 4. Even exponent, negative leading coefficient. And then we say that as x is increasing, so as x gets really, really large, your y value will still be decreasing. And as x will decrease without bounds, or will go to negative infinity, your y will still go to negative infinity. Right? So your graph will be going both ways, going down. Now, let's go to the zeros of the polynomial functions. So the values of x for which f of x are equal to 0 are called the zeros of the function. The same values are also called the x-intercepts, the real roots or solutions, and the real solutions of the equation appear as x-intercepts on the graph. And to find the zeros of the function, set the function equal to 0, and solve for x. So we have here a couple of examples. If we have here a, which is f of x, is equal to negative x to the fourth minus 4x cubed minus 4x squared, we set this equal to 0. And then after which we solve for the zeros of the function by factoring out negative x squared, and then factoring it furthermore, we can factor out your x squared plus 4x plus 4 into x plus 2 squared, and solving for your x, then we get the zeros negative 2 and 0. Now the same thing is true for the second example. So we set it equal to 0, and then we'll factor it out by grouping. So you factor it out by grouping, factor out the common factor of the first group, and then factor it again by grouping, and you will have the final factors to be x plus 3, x plus 1, and x minus 1. So the zeros of the functions are negative 3, negative 1, and 1. Now, notice that some of the factors, like in the first example, actually, this one here are two factors of 2 and two factors of 0. So if I had to write it out, it should be like this. So there are some factors with multiplicity, meaning they can repeat in your zeros. So there's 2 of them of -2, and then 2 of 0. Right here. All right, so if x minus r to the n is a factor of the polynomial f of x, then x equals r is a 0, and r is a multiplicity of n. So when the multiplicity of is 1, we know that it will just cross the behavior of the graph at its roots, or at that 0 will cross the point. But if n is even, then the graph of f of x will be tangent, or it touches at the point x equals r on the x-axis. When n is odd greater than 1, so say for example 3, 5, 7, and so on, then the graph of your function will form a caret, or it flattens, like your x cubed graph at the point x equals r. So this is how it's going to look like. So it crosses when it's 1. It will just cross at x equals r. It will be tangent, so it will just touch at the x equals r, and then it forms a terrace when it is x equals r and multiplicity of 3, 5, or 7. And another thing that we need to talk about is about the maximum and the minimum of the of the graph of polynomial functions. So in the graph of a polynomial function, we call the high point of the graph the local or relative maximum. Now, low point in the graph, local or relative minimum. We call the highest point of the graph global or absolute, and lowest of the graph as global or absolute minimum. So what's the difference between the two? Well, the local maxima, whether it's the maximum or the minimum or the relative, they are just the highest or the lowest in a particular interval of x. It's not the highest or lowest of the entire domain. So say, for example, in this particular graph that we have here, 2 here is just the highest value in this particular interval of x. But it's not the entire domain, because see, it can go on forever. So there will be no highest, because you can go on forever all the way to the top or all the way up. Now, another thing here is in the interval of these x's right here, 1 is also the highest. But it will only be just for that particular interval of x values. So we say that the local maxima here, so there's 2 of them, will be at 2. Well, the local maxima is 2 at x equals 3 and 1 at x equals 2. Same is true for the minimum values. So if you look at here, the -3 is the minimum value for this particular interval of x values. And then it's also -1 for this particular interval of x values, but not necessarily for the entire domain. So which means that we say they are the local minima. -3 at x equals -1, and -1 at x equals 4. There are no global maximum and minimum now. Because again, we said that this graph can go on as far as it can and go down without bounds. And that's all for the introduction of your polynomial functions.